The Docker privileged flag entirely dismantles container isolation. It presents an immediate avenue for complete host operating system compromise. When this flag is enabled, the container receives all Linux capabilities. This includes dangerous permissions like system administration and raw network access. Running the capabilities show command inside the environment exposes a completely unmasked bounding set. No restrictions are placed on kernel interactions. Standard containers mask highly sensitive paths within the process and system file systems. Privileged mode leaves these critical kernel interfaces wide open. The container device directory gains direct access to all host block storage devices. This allows the inner process to see raw disk partitions.
A system analyst can list the contents of the device directory to locate the primary host storage volume, typically labeled disk 0 or drive alpha. We can create an arbitrary directory inside the container and directly mount the host root partition using standard file system layout parameters. Once mounted, the entire host operating system directory structure is fully readable and writable from within the supposedly sandboxed container application. An attacker can append a new privileged user entry directly into the mounted host writable password and shadow configuration files. Alternatively, writing a malicious reverse shell command string into the host cron scheduling directories ensures execution by the host system root daemon.
When raw block devices are restricted, attackers turn to control groups version 1 architectures. This highly technical escape exploits the kernel notification system handling empty task lists. The exploit sequence starts by creating a temporary directory inside the container file system to act as a dedicated control group hierarchy mount target. We execute a mount command targeting the control group file system type, explicitly requesting the remote direct memory access or tracking subsystem to isolate our actions. Inside this newly mounted control group directory, we use the make directory command to instantiate a child control group node, which inherits subsystem controls.
We must configure this child node to notify the kernel when it becomes empty. We achieve this by writing the character 1 into the notify on release file. The release agent configuration file specifies an executable path that the host kernel will run automatically as soon as the last process in our child group exits. The fundamental challenge is that the host kernel looks for this release agent executable path relative to its own root file system layout, not the container layout. To locate where our container files sit on the host, we parse the mount info file inside the process self-directory, extracting the exact overlay storage path.
By concatenating the host overlay upper directory path with our internal container script location, we obtain the absolute file path visible to the host operating system kernel. We write this carefully calculated host path directly into the release agent configuration file located inside our temporary child control group node directory structure. Now we create the actual payload script inside our container. It contains a standard bash command sequence designed to spawn a reverse shell back to our workstation. The payload script must be executable by the kernel. We change its file mode bits using change mode plus execution arguments to ensure successful background processing.
To trigger the kernel notification, we must add a process to our child group and make it exit. We write the character 0 into the tasks file. Writing 0 inserts the current shell process identifier into the control group. Because that process immediately moves on, the task count instantly drops back down to 0. Detecting an empty control group with notifications enabled, the host kernel fetches the registered release agent path and immediately executes our upper directory payload script outside the container namespace, running with full host root authority and completely detached from standard isolation controls.
On our external listening workstation terminal, the incoming network connection instantly establishes a raw interactive shell session operating outside the sandbox boundaries, providing a system analyst or an attacker full administrative command execution capabilities over the primary host operating system deployment. Another highly sophisticated container breakout mechanism leverages the kernel core pattern configuration interface. This system parameter regulates how the hosting machine processes application crash events and regulates where core dump files are written when unhandled memory exceptions occur inside active running programs. Because the target container is operating in fully privileged mode, the process system kernel core pattern file is completely writable. We can replace its contents by passing a pipe character followed immediately by the specific target host path of our execution script. The leading pipe character instructs the host operating system kernel to pipe the core dump output directly into the specified script for runtime analysis. By pointing this path to our container overlay storage location, we force the host to execute our containerized script. To activate this pipeline mechanism from within the container, we execute a simple program that intentionally induces a segmentation fault or handles a termination signal incorrectly, thereby triggering an immediate application crash sequence that forces the kernel to process a brand new core dump. When the process crashes, the host kernel manages the core dump event by executing our registered payload script completely outside the container sandbox infrastructure, immediately granting the remote listener workstation an active interactive console session with absolute administrative privileges on the target hosting machine. Full privileged status also grants the highly critical capability system-intensive module permission. This explicit flag allows processes running inside the isolated environment to load arbitrary compiled binary code directly into the active host kernel space, completely bypassing userland constraints. We compile a native Linux kernel module targeted specifically to the precise version string and architectural layout of the hosting machine, embedding a standard user mode helper execution sequence inside the module initialization routine to spawn an external process during loading. Executing the standard insert module utility inside the container with our newly compiled binary file inserts the code straight into the running host kernel space, completely bypassing every traditional file system restriction, active container sandboxing filter, and container runtime isolation parameter. The newly loaded kernel module automatically executes the user mode helper system application programming interface, triggering a background reverse shell script on the main host layer that opens a network channel directly back to our automated security monitoring workstation with absolute root clearance.
When the container configuration shares the host process identifier namespace, the explicit permission named Capability System Trace allows an analyst to attach to, read memory from, and completely control any active process running on the underlying host operating system tier. We search the process tree to isolate a process identifier belonging to a highly privileged host system daemon, such as systemd or the secure shell daemon, both of which operate with master-level administrative access rights on the underlying hosting tier. Utilizing the process trace debugging system call interface, the container exploit process attaches directly to the running host daemon, halts its operational cycle execution, and systematically injects customized assembly language shellcode payloads directly into its volatile memory space. We alter the host process instruction pointer register to point directly to our newly injected memory segment, forcing the high-level host daemon to execute our interactive reverse shell commands before it can resume any of its standard background operations. Eradicating these profound architectural security vulnerabilities requires structured operational auditing. System analysts must inspect all live orchestration configurations to verify that the dangerous privileged parameter is explicitly set to false across all production and testing application deployment manifests. Instead of providing broad, unmasked administrative permissions, isolate the precise low-level kernel interactions required by the software workload and explicitly add only those specific capabilities, such as system administration or network administration, minimizing the overall blast radius. Implementing distinct user namespaces across your container clusters ensures that the root user account executing inside the sandbox maps directly to an unprivileged, non-administrative user identifier on the host operating system, rendering breakout attempts completely harmless. Configuring a read-only configuration on the container root file system prevents malicious entities from writing temporary exploit payload binaries or altering runtime configuration scripts, effectively blocking the injection steps necessary to complete a successful control group escape chain. Apply tailored secure computing filter profiles to restrict access to high-risk system call interfaces like process trace, mount, and insert module, ensuring that even if an administrative user runs a container, they cannot trigger low-level kernel mutations.
Resilient container security depends on removing broad privileged configurations, enforcing granular capability allocation, applying strict secure computing filters, and continually monitoring running tasks to guarantee that the isolation boundary between the application and host operating system remains unbreakable.